Now, Kartik will talk about order policy enforcement and limitations and circumvention. We set it up properly. The screen is visible. Please go ahead.
Can you guys hear me? No?
Again, louder.
Can you guys hear me?
You need to keep it higher.
Can you guys hear me now?
Yes, good.
All right. Thank you so much, Juliana and Christian, for inviting me. I'm very happy to be here. And today I'll be talking about order policy enforcement, limitations and circumvention. So this is joint work with lead authors Saresh Dwadwa, Luca Zanolini, Aditya Asgaonkar, Francesco De Amato, and Fan Zhang. So typically, when you think of consensus protocols, you talk about honest majority assumptions. And I'm going to talk about a very different property with respect to order policy enforcement. And what I'm going to talk about is, when you're looking at a very different property, the set of assumptions that the set of trust assumptions that you make would be very different. So let me start off with something that you already know, with state machine replication, where a group of parties agree on a sequence of transactions submitted by external clients. And the two key properties that you're looking for intuitively are safety and liveness, where safety says that any two non-faulty parties do not learn a different sequence of values. And liveness says that a transaction proposed by a client will eventually be executed by every non-faulty server or non-faulty party. So let's say you have these transactions coming in one at a time. And once these transactions arrive, these parties will agree on a block of transactions, and they will output it. And even within this block, there's going to be an ordering where over here in this example, the gray transaction precedes the yellow transaction and so on. And there can be a new set of transactions that come in to form the next block and so on and so forth. So if you looked at the animation that I showed you very closely, you'd have seen that there was a specific ordering in which these transactions arrived. So the gray transaction arrived at all parties before the yellow did, and similarly for blue and red, right? And in that sense, very intuitively speaking, one would argue that it is fair that the block was ordered in this fashion. A natural question is, well, if the block was ordered differently, if the red transaction appeared before the blue one, is that fair? Is that okay? Well, the answer to this question is, it depends whether it's okay, right? You can ask maybe a lower order question, are these reordered transactions actually independent of one another? For instance, let's say the red transaction over here represents a world where, party A made a transaction with party B, and let's say the blue transaction is one where X paid Y, then these are entirely independent objects. And at that point, maybe reordering is okay. But a different situation can be where these are generated by two different honest clients on a dependent object, where they're affecting the same object, but they were generated independently. And in that world, it's not very clear as to whether it is fair to reorder them or not. What people would generally agree is that if the blue transaction came in, and after that, the red transaction was generated by an adversary after seeing the blue transaction, that can be bad. So this is what is typically referred to as front running. And why is that bad? Because from an adversary's perspective, you would want to do this because you would earn money. But from the perspective of the blue transaction or the client who made that blue transaction, you can actually lose something in the process. So front running is one example of such an attack, and there are many others, such as sandwiching, censoring transactions, and so on and so forth. So this is a known problem for the past 3 or 4 years. There has been a lot of work on this. And there are, at a very high level, there have been two high-level approaches to what we call data-independent order policy enforcement. So over here, we call it data-independent because while ordering, you're not looking at the contents of the transactions itself. Okay. So the first approach is what is referred to as order fairness, where the transactions are ordered based on their arrival times. So Equitas, Themis are examples of order fairness protocols. And over here, the goal is to just ensure correct ordering. So if you go back to the question that we were asking earlier, whether the transactions are independent or not, that question does not even appear because the transactions are just ordered based on their arrival times. A second alternative is what we call content oblivious ordering. And over here, your user transactions are hidden from the parties ordering them. At a very high level, you're hiding the transaction, so the adversary who's ordering them does not know what these transactions are. And that is why they cannot adversarially order some of their own transactions before an unknown transaction. So in the class of questions that we were asking earlier, red transaction never, so the adversary generating the red transaction would never see the blue transaction while ordering. So in that sense, front running is not possible. So you're trying to avoid the third of the three. So both of these approaches are attempting to prevent reordering attacks. And the question we are asking over here is, well, do these protocols actually give you that property? Do order fairness protocols and content oblivious ordering protocols actually prevent reordering attacks? I mean, at a high level, these protocols are designed to do exactly that. Then why am I asking this question? The concern is that, over here, for these protocols, their correctness relies on a majority of parties being honest. And in practice, if you think about the attacks that we considered, it's based on the rationality of the parties. Reordering benefits them in a certain way. And if these parties are rational, then they would want to do it. So the question actually is, are these protocols secure when these parties are rational and not necessarily honest, or there being an honest majority? And this is what we're going to focus on today. So in the talk, I'm going to talk about two different parts. So the first part would be, I'm going to talk about for known order policy enforcement protocols under rationality assumption. I'll talk about an impossibility result where, I think because I want to talk about known order policy enforcement protocols, I'm going to talk about a framework of these protocols and show that, existing protocols are not secure if the parties are rational. And second, I'm going to talk about how we can circumvent this impossibility. So the constraints of the impossibility result is what's going to help us in circumventing it. So to talk about the framework, let me first talk about an example within the framework. And then, one such example is a content oblivious ordering protocol, which is threshold encryption based. This is what is used by Shutterized Beacon Chain as well as Furvio today. So you have these ordering parties. The first step that you perform is an initialization, where you create public keys and secret keys for each of these ordering parties. And then the next step is this transaction submission step, where the user encrypts a transaction and submits them. So the yellow transaction is the actual transaction, and the boxed yellow transaction is an encrypted transaction that is submitted. And similarly, you will have other transactions that are submitted to the system. The next step is transaction inclusion, where these parties agree on an ordering of transactions, and this ordering can really be arbitrary over here for this content oblivious ordering protocol. And finally, once it has been agreed upon, you can decrypt these transactions using their respective secret keys. So the crux of the intuition behind such a protocol is that this ordering happens while the transactions are encrypted. So you cannot put in so you can actually put in an adversarial transaction, a red transaction over here, but when you're doing that, you're not looking at other transactions, for example, the yellow transaction, which is at the bottom. So more generally, you can actually capture, it turns out, existing order policy enforcement protocols in a similar manner, where in an initialization step, you're setting these public and private parameters. And then there is this transaction submission step where user submits transactions. This can be an interactive or a non-interactive process. It may be the case that all parties are participating or a subset of them are participating. We assume that users are ephemeral. That is, once a user comes in, submits a transaction, and once the transaction is submitted, the user can go away. This is a desirable property for any blockchain. And finally, parties may capture local state at the end of this, for example, the time at which the transaction arrived or other metadata. The next step is this transaction inclusion step, where you're executing some protocol to order. So fair ordering protocols execute their fair ordering protocol in this particular step. And other protocols, for example, content oblivious ordering protocols can perform some sort of random ordering or arbitrary ordering over here. And finally, the last step is what we call transaction reveal, where you're decrypting transactions. This is an optional step from the context of fair ordering protocols because they don't need to do it. So there are two additional constraints that I'll describe which need to be satisfied in this protocol. The first property is called the binding property. And the binding property says that a transaction executed is the one that is submitted to it, right? So if I say I want to buy 100 tokens of token A, then that is the one that is executed. This is like a very straightforward property that any system should have, but I'm going to touch upon this property a little later. That's why I'm describing it here. And second, we assume that once this transaction has been submitted, there is no modification of state after the transactions are ordered. So explicitly, we are ruling out, properties like time lock encryption from the protocol. And finally, something that I described in the previous slide as well, but I'll mention it again, and that is ephemerality of clients. That is, a client is not required to stay after submitting these transactions. So given this framework, what we show is an impossibility result, which says that, if you can order in a way that you do not satisfy a given policy and you can gain more in the process, then you will actually do it. In other words, if there exists a protocol pi that is supposed to follow this order policy enforcement framework, enforcing some policy P, and it is run by a set of rational parties, then for a given input, if there exists a way to reorder the transactions and earn a higher utility by not satisfying P, then pi will not follow P. Okay, so the third part over here is a little imprecise, so let me try to explain it a little more, but I'll still stay informal. So let's say for this policy P, we have this input stream T1 to TL of transactions. And let's say among all possible sets of orderings that are possible with this policy P, let's say tsec is an ordering that gives you the maximum utility. And let's say you can generate this tsec prime by running some sort of an extract function on this input in such a way that tsec prime is not a valid output for the original input of T1 through TL, but it is a valid input for some different input stream. And in such a way that in that world, you can actually get a higher utility, a utility higher than U. Then an attacker will actually prefer to output tsec prime, even in a world where your input was T1 through TL. So this function extract is intuitively what you would think or what people think of as this MEV extraction function. Okay, so the crux of the proof for showing this impossibility is in two parts. First is to show an attack algorithm that you can that we show, and then we argue that if you run this attack algorithm, then no one can hold any party, no user can come back and say that this attack algorithm actually happened. Okay, so our attack algorithm is the following simple algorithm, where we run this in a TE or a trusted execution environment, where all of these parties actually reveal the transaction within the TE. Okay, it's not publicly known, but it's only known within the TE. And they basically run this extract function on the transactions. So in practice, you can just run an extract function which combines the strategies for all possible extract functions that can exist. And then within the TE itself, they'll replay these extracted transactions and order the new set of transactions that they receive, and finally publish the new state which satisfies this policy B in the other world. So with this, what we can actually show is that a world one where this attack was actually performed, where your input was some T1 to TL, and you ran this attack algorithm on your input. This world one is actually very similar to a world two, where your input was a different set of T1 prime to TL prime, and your output, a potential output that satisfies this policy P, was tsec prime. And let's say in this new world, your utility was higher. Your utility for these parties was U prime greater than U. Then, because no user can actually prove that parties deviated from the protocol, that is why you can actually, so all of these parties can actually enjoy this high utility U prime in world one as well. And for that reason, they would actually perform this attack in world one. So with that, let me move on to the second part of my talk. So there is this impossibility under certain constraints that exists. So how can we actually approach this impossibility? So we spoke about two different properties earlier. One is, ephemerality of clients, and second is the binding property. So ephemerality says that a client is not required to stay after submitting transactions, right? And binding property says that a transaction executed is the one that is submitted, right? And it turns out that if we can relax these properties, you can actually circumvent this impossibility result. So let's see how to do that one by one. So if we are relaxing the ephemerality of clients, then we are saying that, well, clients need to stay until the transaction has been added or committed to the chain. And in this situation, the protocol that you'll get is actually very simple. The client will, so the solution is through some sort of a simple commit and reveal, where the client never submits the transaction in any form to anyone. So no one can actually know or reveal the transaction within the TE. The client simply submits a commitment to the transaction, and once it has been added to the chain and committed, at that point, the transaction content is revealed. So this is not ideal because it requires clients to be online, and at the same time, it is not ideal from the perspective of the protocol itself, because clients can be fickle. So if they're not online, then the content may never be released. And second, so one way to circumvent this is to use some sort of TEs to actually escrow this information for performing such a reveal. So the second way to circumvent the impossibility is to relax the binding property. So the question we ask is, well, what if the transaction submitted by the user is not guaranteed to be the one committed and executed? Well, this is like a fundamental property for any chain. You submit a transaction, and that is the transaction that gets executed. You do not want to give this up, right? But what if it's the case that only in pathological cases something else will get executed, but in most cases your transaction will get executed? And the reaction that we're looking for over here is what we call rational binding, where binding holds so far as a specific set of parties or stakers are rational. So in our protocol, we have this designated party called a flipper, who is if this flipper is rational, then the transaction that is executed is the one submitted. But if the flipper is arbitrarily malicious, then that property may not hold. So let's see how we can use this relaxation to actually achieve some sort of order policy enforcement. And the protocol that we have over here is not a generic one, but it is very specific to preventing sandwiching attacks on automated market makers. So I'll take a small detour and explain what automated market makers are and what sandwiching attacks are, and then we'll look at the protocol. Okay, so in automated market makers, you can exchange one quantity or one product for another, or one token for another. And typically, you're exchanging, let's say, some token X for some token Y. And there is an exchange rate that is decided based on the availability of the tokens that you're buying, for example. So a transaction looks like the following, where you're saying, I want to buy Y tokens of A for X tokens of B, and there's the slippage parameter S. Okay, so how do I decide this Y for X for these two tokens? A client can just look at the system, know the value of what of these tokens at this point. How much should I exchange, and based on that, it can decide this exchange value, right? But between me submitting this transaction as a client and it being added to the chain, this value may fluctuate a little bit, and that is why you specify the slippage parameter S, where the client says, or the user says, I should get at least 1 minus S times Y tokens of A. So if this is the property, or this is the transaction we are looking at, here is what a sandwich attack can look like. You have this user transaction. An adversary who's looking at all of these transactions in the system can simply run a transaction just before the client transaction, which basically reduces the supply of A enough so that the client gets the worst deal that it can ever get, right? So it gets exactly 1 minus S times Y. And then you run this user transaction, the client gets, or the user gets a bad deal. And after that, the attacker simply reverses his transaction in what it's buying. And it turns out that in this process of sandwiching, you can actually earn a lot more money. So with our property, with rational binding, what we're trying to do is we are trying to ask, well, we're trying to get into a situation where the attacker does not have all the information it needs to actually perform this attack. We're trying to withhold some information from these attackers. So a question you can ask is, well, what if the attackers did not know the polarity of the transaction itself? So over here, we said it's a buy transaction, but what if this was a sell transaction instead? Then it turns out that there are two things that can happen. One is the attackers will lose money because the transaction is in such a way that you're reducing the supply of A, and if someone else is selling A, the supply goes in the other direction. So in this process, the sandwiching was performed very much for a buy, and if you sell, the attacker is going to lose money. And a second thing that happens is that the user actually gets a much better deal than what it did otherwise, right? So much better than what it was expected to get even without the attack. So the idea over here is, well, can the user use some of this gain that it gets in some situations when the attack is unsuccessful to incentivize a party to actually hide this polarity? And this is exactly what we try to do with our protocol, where the user tries to incentivize some party that we call a flipper, and the flipper is trying to confuse or cheat all of the other parties in the system in such a way that the flipper wins if these other parties lose. Okay, so the flipper is the one who's trying to hide the polarity of this transaction. So I'll go fast, but I'll explain this in 2 steps. I'll explain the intuition in 2 steps. So the first step is, I'm going to assume that your flipper is entirely honest and it will just follow the protocol. And then I'll talk about how to incentivize this flipper to actually do what we want it to do. Okay, so if you had an honest flipper who's a designated party in the system, here is what the transaction submission process would look like. Okay, so as a user, if I want to submit a transaction, let's say I want to submit a buy transaction, then I will simply toss a coin. If this coin B turns out to be 0, then I'll sign and submit the transaction that I'm interested in. If this coin turns out to be 1, then I'll actually, even if I want to buy, I will actually perform a sell transaction over here. Okay, so I'll sign and share a sell transaction with all the parties. In addition, I'm going to share an unsigned bit with bit B with the flipper, so that the flipper knows the actual polarity of the transaction. The reason why I think I'm not digitally signing this particular bit is because I do not want the flipper to collude with the rest of the parties. The flipper has some additional information that no one else has, but the flipper cannot prove it. And from a protocol standpoint, it is you can run any content-obvious ordering protocol now. And the only thing that you would do is that the flipper, after the transaction has been added to the chain and committed, the flipper will come in and reveal this bit B, which is only signed by the flipper, and that would be the transaction that would take effect. Okay, so in particular, my transaction was a buy, but B was 1.
Hai Cosman.
And sell.
No, we have to mute someone also.
All right. So if my transaction was buy and sell was the one that was added to the chain, the flipper can come in and say B equals 1, so the transaction is actually a buy. So it turns out that just by this, you will have 2 properties that we are looking for. So I think because we are assuming honesty in the flipper, it will always reveal the correct bit eventually. Okay, and a correct transaction will always be output. Okay, so over here, this happens because we are trusting the flipper. And second, from an attacker's standpoint, right? I think if you're trying to perform some sort of a sandwich, now their ability to gain any money depends on the ability to guess the polarity of the transaction correctly. For instance, if there's a 50-50 chance that the attacker guesses it correctly, then in some cases it will gain, in some cases it will lose, and eventually it will not have any gain. And this is the intuition why, if it's a 50-50 chance, then the adversary would not want to attack, even if the adversary is rational. So the remaining question is, I think over here we assumed honesty on the flipper. What happens? So how do we actually incentivize the flipper to? Sure, 2 slides. So how do we incentivize the flipper to do the right thing? So the first thing is, flipper needs to be incentivized to not collude. That is, reveal the bit correctly to the attackers. And for this, we incentivize it in a way where whenever the transaction is unsuccessful and the user gets a good deal, the user pays some of this money to the flipper. So in that sense, the flipper is incentivized to actually confuse the attackers. The second part is, well, what if the flipper reveals the incorrect bit where, I wanted a particular transaction, but something else gets executed. And this is where we are relying on, rationality of the flipper, where there is some exchange that happens between the flipper and the user in such a way that if the flipper reveals an incorrect bit, the user can come back and penalize it. So there are parts of the solution that are not entirely practical yet. For example, if I'm trying to reverse the polarity from a buy transaction to a sell transaction, then well, if I'm trying to buy a token, that's fine. But if I don't have the token, I could never represent a sell transaction. So I think so there are those aspects that are not yet ironed out. But other than those aspects, this is like an interesting strategy to deal with a set of rational parties who are trying to come and attack you. So with that, let me conclude my talk. So we spoke about 2 parts. One is, we showed that known existing data independent order policy enforcement protocols are actually not secure when all parties are rational. And then we spoke about 2 ways to circumvent this concern. One is relaxing ephemerality of clients, and second is relaxing the binding requirement for a transaction. So with that, I'm happy to take questions. Thank you.
Questions in the room? Yes.
So you use as an example of an existing OPE protocol, a threshold encryption system like Fervio. And I was wondering what in that example they would have to do to violate the ordering protocol. Do they all have to collude so that they can compute stuff in advance? And if so, are there ways we can penalize them if they get caught colluding?
So I think the impossibility result is basically saying that, I think what we show is an attack algorithm that they would, I think we require a TE to do that. But what we actually show is that if you do it the way we are suggesting, you cannot get caught. So in fact, when we were trying to circumvent this, I think the first set of approaches we attempted were trying to catch the parties who are actually trying to attack. And we realized we could not do it, and that is why we went for an impossibility result. Thank you.
Thanks for the talk. It seems like the mitigation techniques require in both cases to revealing of the information after the ordering. So it's like at the time that I submit my transaction, I might not know what might have been, what exactly might have been previous to that. So can you maybe briefly talk about the trade-offs involved? Because at the extreme, if I want to prevent all of these MEV opportunities, for instance, I might just do like a batch execution, just execute everything with respect to the same price after finding the equilibrium. And people don't like that for various reasons. So what would be the trade-off here, the drawback of this revealing of the information after the fact?
So I think, so whatever is already committed, right? So there are commitments to it. So you cannot reveal something else, right? So the only part over here is where I guess the flipper is revealing this bit, which is new information, right? So if the market shifts in such a way in a direction where, just going the other way, where, it reveals an incorrect bit and it takes a penalty hit and yet it can earn more money in the process, for example, then that can happen in such a solution, because the flipper in that sense has this ability to do whatever it wants. But for the rest of information that is revealed at a later point, there's a commitment to it, so you can verify what is revealed and what is not. Right? But
Thank you again. Thank you.